Yeah. Still we seen the introduction to proof, right? From the section 1. Then direct contraposition, proof, contradiction, what is counter examples, then principle of mathematical induction or strong induction. I think proving of correctness of program, that one point was remaining. Okay, that will take also. Elementary set theory we have seen, right? Then relations, today we'll start with the relations, functions, basic counting principle, permutation, combination, generalized permutations and combinations with and without relations, distinguishable or indistinguishable objects. Okay, so these points are very important as far as theory of computation is concerned, right? So you will have only the assignment on this lab, but these concepts are required for the theory of computation, right? So that is the purpose of to study this subject, okay, in lab, talk lab. Yeah. So we'll start with the relation. What is relation and all? So that is we call discrete mathematics relation. Now here you can see relation, that is a family example. If we consider that is father to son or mother to a son, then father to a daughter or mother to a daughter, the relations, you know. So father son relation, mother son relation, mother daughter relation, and all. Now let us describe this is in terms of the discrete mathematics. Okay. If we take, there are two sets A and B. Okay. So let's take here. The set A having father and mother, and inside B we have daughter and son. Just this is for example, and let us what we have see in the diagram, right? According to this diagram, let us put some relations. Yeah, father to son, then father to daughter, mother to son, and mother to daughter, right? Now here, so this can be further ordered as like this, okay? Yeah. But question is here, this is said ordered pair, as you cannot reverse or change the order, right? For example, son cannot be inversely related to father of father, okay? So here this is an ordered pair, that is from higher hierarchy to lower hierarchy. Any ordered pair, that is not always reversible, okay? So the question is what again? Can we relation between son and daughter, right? So here answer will be the no. Why we can't create a relation between son and daughter? Because they are element of the same set. Yeah, we have seen set B we have taken and set A we have taken. In set B we have son and daughter, right? So we can't have the relation between, because they are in the same set, okay? So we make a relation between the elements of different set, right? So answer obviously will have, that is no, because they are element of the same set. Some of the definitions we'll consider. Already you know what is meant by relation, yeah, how to represent it, but We'll revise once again. Now any set of ordered pair defines a binary relation or simply a relation, right? Binary relation represents relationship between elements of two sets. If R is a relation, a particular ordered pair x comma y inside the bracket that belongs to that relation can be written as x r y, x small x capital R small y, and can be read as x is in relation to R with y. Okay, x in relation to R with y, or x is in a relation with y, right, through R, like this. So how to write it? X comma y that belongs to capital R, that is written as x r y, or x is in a relation to R with y. That is simple definition of relation that everyone knows. And the relation examples: plus the relation greater than for real numbers is denoted by the greater than symbol if x and y are any two real numbers such that x is greater than y, then we say that x comma y that belongs to this greater than this relation. Yeah, just the relation is this one, greater than symbol is the one relation we have, and that relation R is equal to, or relation is equal to, R is greater than is here relation such that, sorry, x comma y is the set such that x and y are the real numbers and x is a greater than y. So this here already we have seen these representations, right? This symbol is used for the represent such that and this method of representation we call as a set builder method. Okay, in the theorem competition you have seen that. Okay, so domain and range of a relation. Domain, what is meant by domain, what is meant by range, and what is the relation in a relation. Domain, set of all first numbers of the ordered pairs. In other words, the domain is all of the x values. Okay, and range is a set of the second numbers in each pair. So the y values so that is a range is a set of the second numbers in each pair, right? So that is, you can say here range of example 1, 22, 34. This is a range. And domain, what we call set of all first numbers of the ordered pairs. The domain in all of the x values, that is 0, 3, 90. Here we have a set 0, 1, 3, 22, 90, 34 with pair, right? And the domain and a range. So just remember the concept with the help of example. Now list the domain and the range of the relation. Here domain, obviously you can range. Here we have a set that is minus 3 3 with pair 3 2 sorry 0 2 3 3 6 4 7 7. Now here, even though the number 3 is listed twice in the relation, you only note the number once when you list in the domain or range. Okay. So domain is a minus 3 0 3 6 7, and the range is a 3 2. Second numbers is a 3 2 4 and 7. So representation for set S, that is a D of S is equal to X, such that for all Y, or there exists Y X comma Y as X comma Y belongs to S. And R of S is equal to Y, such that for all X, or there exists X as X comma Y belongs to S. Just a mathematical representation of any set you can take. Okay, so this is all about just a mathematical representation, what is meant by a relation. Definition of a function. A function takes an element from set and map it to a unique element in another set. That is called as we say one kind of definition of function. It takes an element from a set and maps it to a unique element in another set. Okay, so let's here we have two domains, domain R and domain Z. So function F maps R to Z. Okay, that is the function F maps R to Z. Now here we have a pre-image of that is a 4, that is okay, and here image of 4.3. Yeah, so because of mapping, yeah, so that is F of 4.3 we call. Given any set A comma B and a function F from or we call as mapping A to B. So F of A tends to B is an assignment of exactly one element. Okay, so F of X that belongs to B to each element, such that what we can say X belongs to A. Okay, and if I have any element that is Y that contains a from X tends to B, if it is there Y it is there, then Y belongs to B. Okay, so there is a graphical representation of function, that is A element of A set is functionally relation with B, right, from set B. So some kind of terminologies we have, that is if f of f is a function of A tends to B and f of A is equal to B, where A is belongs to A and B belongs, small b belongs to capital B, then A is a domain of F. Okay, so how to, what are the terminologies and how to get it? A is just read as a domain, B is also a domain, that is we can call it as a codomain also of function. B is the image of A under F. Okay, so B is called as is the image of A under function, and A is the pre-image of B under function. These are the some terminologies we can read. In general, B may have more than one pre-image, and the range R subset of B, right? So we have seen a range of range and F. What is meant by range and domain, right? So range R is subset of B of function such is B such that for all there exists A as F of A is equal to B. Okay, so like this you have to represent the range. The domain and codomain example, that is a class grade function. It is domain and codomain. Here we have some names in one domain, and codomain, that is A, B, C, D, F. Okay, a class grade function, that is relation, direct relation, right? Ashna have a grade, number have a grade, rank have a grade and all. A pre-image of 1 or the image of A. So the image of A that we have count here, that is 1, 2, 3, 4, 5, right? And its pre-image, that is we call here A1. For B here we have, right? Here is the, you can see E. So number of characters is counted here, right? So a string length function, that is we call as a string length function. So in the string length function, you can say for a pre-image of A, we have a image of that pre-image. So let us take one example. Suppose F is a function mapping students in this class to the set of grades. At this point, you know, function domain is, yes, what is the function domain? Already we have given a range here, that is done. Range in a relation we have seen, that is not a range in a relation. So here the range, there is a function from A to B, right? Then range is a subset of B only, of F, and B is a, that is called as a, we take a B only. Okay, here it is a B for such that for all A, F of A is equal to B. So in this A, B, C, D, E set, the codomain we have already, right? And its range is because we have a set of grades, right? And not specific again. But if we turn out all grades into A and B's, then we have a range of it, that is a E comma B. Okay, and codomain is ABCD. So that is all about here function. Permutation of a set of distinct elements in an ordered arrangement or sequence. Okay, let us understand the permutation and R permutation. What is a permutation of a set of distinct elements in ordered arrangement or sequence of these elements? An ordered arrangement of R elements of a set is called as an R permutation. Okay, so an ordered arrangement of R elements, so it is called as a R permutation. And the simple permutation definition is a set of distinct elements in an ordered arrangement or sequence of these elements. These are the simple definitions. Three permutations of the set ABC. Right. So permutations we have A, B, C, A, C, B, or B, A, C, B, C, A, C, A, B, C, B, A. Right. All these are permutations. If we have three elements, we have total 6 permutations. Yeah. So how many permutations of an element here are, right? Let's calculate by the formula permutation rule. Given a set of n distinct elements, you wish to select R elements from n and arrange them in R positions. The number of permutations of n elements taken R at a time is equal to, that is n factorial divided by n minus R factorial, right? So understand the theorem first. Given set of n distinct elements, we have 3 distinct elements. You wish to select R elements from n and arrange them in R positions. Okay, and the number of permutations of n taken R at a time is equal to, so put the values here. We have a 3 set of elements in the previous example. 3 factorial divided by 3 minus 3 factorial. So 0 factorial is 1 and 3 factorial is a 3 into 2 into 1, that is we get the 6 value here. Okay, so keep in mind this relation. So in a race with 8 runners, how many ways can the gold, silver and bronze medals are awarded? Yeah, this is I think question. Yeah, can you? Anyone? In a range with 8 runners, we have 8 runners, and how many ways can be gold, silver and bronze medals are awarded? Yes, anyone can give the answer?
Sir, 336
8
ways.
factorial upon factor.
8? Yeah, I think give any one. Just
8.
8. R value is a 3.
3.
Yeah, so we have to put 8 factorial divided by 8 minus 3 factorial.
5.
Yeah, 5 factorial, right. So 8 factorial. So make it 8 into 7 into 6 into 5 factorial. So 5 factorial will get cancelled and we'll get
252.
250.
336. 336.
Just take a one answer from.
336.
Yeah, okay, good. If 8 into 7 into 6, that is the answer. Now you calculate. So a salesperson has to travel 8 cities but must begin the trip at a specified city, and he can visit other 7 cities in any order. How many possible orders for the trip can the salesperson have? Yes, solid. Yeah, one kind rule, partition rule we have in permutation counting. The theorem is the number of permutations of n elements where there are n1 objects of type 1, n2 objects of type 2, and nk objects of type k is n factorial divided by n1 factorial, n2 factorial, and nk factorial. And here we have to note that n1 plus n2 plus dash dash nk is equal to, that should be n. So it's a simple theorem. So how many ways are there to rearrange the letters in the word? Yeah, so what is the question for this? So what is the answer? And second, we have how many n bit sequences contains exactly k ones? Yeah, so these two questions we need to answer. Yeah, then we have a combination, right? Permutation is here. We'll first question answer. So count B, count O, count K, count E, count P, and R, and calculate it. Combinations. Uh, Combination of a set of an ordered selection, right? Sets elements. So in ordered selection of R elements of a set is called an, we call R combination. Okay. So we don't have any order, unordered. Okay, unordered selection. That is we call combination. So R combinations can be interpreted as the subset of the set with R elements. In many ways, the question we have. So how many ways can I select 5 books from any collection of 100 to bring on vacation? Let's solve this. And what is the number of k element subset of an element set? Because here order is not important, right? In how many ways I can select 5 books from any collection of 100 to bring on vacation, okay? So let us say theorem. Give a set of n distinct elements you wish to select r elements from n, and then the number of combinations of r elements that can be selected from an n element is equal to n factorial divided by r factorial into n minus r factorial. So total number of possible arrangements divided by number of ways any one set can be rearranged. Yeah, right. So the number of possible arrangements divided by the number of ways any one set can be rearranged, that is equal to n divided by n minus r factorial divided by r factorial. That is the same thing. So this one is a Eisenhower principle. Eisenhower theorem is what? Let k be an integer if k plus 1 or more objects are places into k boxes, then there is at least one box containing 2 or more of the objects. Okay. So let's understand it. K in an integer, okay, and k plus 1 or more objects are placed into k boxes. Let us take any example. We have 5 boxes, and 5 and more objects are placed into these 5 boxes. Then there exists at least one box containing 2 or more of the objects, right? So that is the Pigeon principle. Proof here. Suppose that one of the k boxes contain more than one object, then the total number of objects would be at most k, and contradiction we have since there are k plus 1 objects. Okay. So take now the examples. Given two non-empty sets x, y, where mod x greater than mod y, then for every function f of x tends to y, there exist two different relations of x that are mapped to the same element of y. So among any group of 367 people, there must be at least 2 with the same birthday, right? And how many students must be in a class to guarantee that at least 2 students have the same score? The exam is graded from 0 to 100 and no half points allowed. Okay, these are the examples. This one is generalized Eisenhower principle. If n objects are placed into k boxes, then there is at least one box containing at least n by k objects, right? Yeah, suppose we have 10 objects and let's 5 boxes. Oh, yeah, then take an example. Put n boxes in front of you and 10 objects and 5 boxes. Okay. So 10 divided by 5 if we take, so 2 objects, at least one box should have the n by k objects, obviously, right?